Now, this is going to be a much more difficult question. This one says we have large metal bars being driven into the ground using a heavy falling object. The falling object has a mass 2,000 kilograms, and the metal bar, which is right here, has a mass of 400 kilograms. The object strikes the bar at a speed of 600 meters per second. Sorry, 6 meters per second. I promise I can read. It comes to rest on the bar without bouncing. The result of the collision, the bar is driven into the ground to a depth of 0.75 meters. Okay, first we want to find the speed of the bar immediately after the object strikes it. Now again, we're going to go through our reasoning. What's happening here? Well, we have a collision. There's a collision of this big mass which is hitting that small bar. Well, small, 400 kilograms, but small compared to the big one. All right, so that's one way to kind of say, well, there's a collision. It's probably going to be momentum. All right. You might be able to start thinking about energy, but again, because there's a collision, we really want to stay away from energy, suvat, all of those other things, because energy usually is not considered in those situations. We don't know that it's elastic. It doesn't say that, so we shouldn't assume it. All right, so let's go ahead and we'll go with momentum. So we're going to take the momentum final. So sum of the momentum's final should equal the sum of the momentum of initial. So, or initial equals final. Sorry, I did a little bit backwards there. It really doesn't matter, does it? But I know we've been doing it this way. So initial equals final. So initially we've got the big object again. So the momentum of the big plus the momentum of the small should equal the momentum of the big finally plus the momentum of the small finally. Because I just have these two objects, the big one and the small one. So the momentum of the big one, let's see, we've got 2,000 for its mass times its velocity. It says it strikes the bar with a speed of 6 meters a second. Okay, plus the initial, the bar is at rest, so we can put a 0 there. And then the final, let's see, it says we don't know that. But it does say that it comes to rest on the bar without bouncing. Okay, so that's going to be like that first question we saw, right? Comes to rest without bouncing, which means the two objects are connected, they're moving together. And so here we're going to have our mass, which was 2,000, times its final velocity. Man, I'm off to date. And then this is going to be plus the momentum of the small, which was 400 times its final velocity, which is the same velocity because it came to rest. They're moving together, right? That's what it said right here. Comes to rest on the bar without bouncing. All right, so now we should be able to solve. We're going to go 2,000 times 6, which will give us 12,000 plus 0 equals 2,400 VF. And then we should be able to go 12,000 divided by 2,400, and we get 5 meters per second equals the final velocity. There we go. 5 meters a second, final velocity. Awesome. So that's the answer to letter A. Now we move on to letter B. Determine the average frictional force exerted by the ground on the bar. Okay, so we've done this situation where the object collided with the bar. Now, what actually happens once that object collides with the bar? Well, the bar hopefully starts to move down into the ground, right? But because there's mass down here and because there's mass on the side, there's some frictional forces, some opposing forces that make that bar slow down, right? If you've ever been near a construction site, you see this. They take a big, huge hammer, and they take this big pylon, and they drive it into the ground with this big, huge hammer or mass. They just keep pounding and pounding and pounding, and it moves it little by little. But because of the friction with the ground, it slows down. It doesn't just go whoop and go straight into the ground. So it takes time. There's a bunch of friction there. So what we're going to do is we're going to assume an average frictional force. Okay? Now, they did give us another piece of information here, right? It said, as a result of the collision, the bar is driven into the ground to a depth of 0.75 meters. Now, there's actually two ways to go about this, okay, you can look at it from two different perspectives. One is we can look at the perspective of energy, right? When this big block hits the small block gains some velocity, right? So if it gains velocity, it then has kinetic energy. So my small bar now has some kinetic energy. Now, when the small bar has kinetic energy, what happens to that kinetic energy due to the friction? Well, the friction causes it to lose kinetic energy. So what is the friction doing? The friction is doing work, right? The friction is doing work. So if the friction is doing work, the friction is taking energy out, right? Well, how much energy is the friction taking out? Well, it's taking out all of the kinetic energy. So if you calculate the initial kinetic energy, then you can calculate the amount of work that's being done, right? So why do I care about work? Well, we care about work because we know that the formula for work is correct. Force times displacement. And it gave us a displacement of 0.75 meters. So let's try it that way first, okay? We'll go ahead and find the kinetic energy. 1/2 times the mass times the velocity squared. So that's going to be 200 times 25. What's 200 times 25? It's 5,000. The 5,000, which is the amount of work. That's the amount of kinetic energy. Because it goes from this to 0, then we know that the change in the kinetic energy is 5,000 joules. That's the amount of work being done by friction. So the amount of work being done by friction, 5,000 joules, should be equal to the force times the displacement, which we said was 0.75 meters. And so we go 5,000 divided by 0.75. And we get 6. And again, let's see, it looks like I got two sig figures here and here. So we're going to go ahead and say 700, not joules, because this is force, so we need to go newtons. Again, recognizing that all of those units are already in SI, and so my answer will give me SI units. All right, so we did the average. That's the force done by friction, because friction is the non-conservative force causing the loss in energy. Now, I do want to show you how we could do this in a different way. And you may have guessed, we could have used SUVOT. Now, we're okay with using SUVOT because it asks us for the average frictional force. Now, if we're looking for an average frictional force, we're looking for an average acceleration. And so, therefore, we could use SUVOT. They give us a displacement. The displacement is 0.75 meters. They give us a initial velocity, right? Sorry, that's a U. So the initial velocity is the velocity that the bar had when it started moving, which was 5 meters a second. Okay? Remember that this has to be situational. You cannot use the velocity before the block hit, because then you have a collision, which during the collision energy is not conserved. So we're using here the time, and that was for this one as well. We're having to use the time period when the energy is conserved for. So that is after the collision of the block, the instant that the block collides until it stops. Energy is conserved during that time period. Okay, so that was what we used over here as well. So we're going to go the final velocity, it's going to come to rest. So 0 meters per second. Now I'm going to give you a chance, pause the video, and decide which SUVOT to use and try to make sure you get the same thing. Go ahead. So hopefully you did something like this right here. You said F equals ma. So the we getting ahead of myself. Your SUVOT equation, we choose this one because we don't know anything about time. So we use our final velocity, initial velocity, and displacement to be able to get the acceleration. Once we get the acceleration here, then we are able to use that acceleration of 16 points repeated sixes to calculate the force of friction. So acceleration here, of course, is due to friction. So force equals mass times acceleration. The mass of my bar was 400, so 400 times 16.666, again, into significant figures, gives me my answer of 6,700 newtons, which you will find is exactly the same answer that we got before. So the initial part, right, the initial part up at the top, yes, this had to be conservation of momentum because it was a collision. The part afterwards, you had some liberty because it was asking about an average force. And an average force gives you the opportunity to look for different things because we assume an average acceleration, so acceleration is constant. And it also then allows us to say, well, the force is doing work, and so we can do it through that method as well. All right, so hopefully that's enough. Use these ideas to get you moving on your homework tonight, and good luck.